In this video, I introduce Bayesian face recognition. Bayesian face recognition obtains a probabilistic similarity measure using Bayesian belief, in which the image intensity difference I1 minus I2 characterizes a face appearance variation. Two classes of facial image variations are defined as intra-personal variation, omega I, and actual personal variation, omega E, using two likelihood probability conditioned on omega I and probability conditioned on omega E. Bayesian face recognition model estimates a similarity score S between a pair of images I1 and I2, which is defined here. Maximum posteriori is used to compute the similarity measure, namely two images belong to same identity if probability of omega I is larger than probability of omega E, or the similarity score is larger than 0.5. Alternative probabilistic similarity measure is computed by using likelihood, which is a maximum likelihood estimate recognition. The details are described graphically here. Principal component analysis is used to divide the n-dimensional vector space into two subspaces, namely principal subspace F and the orthogonal complement F bar. F is the m-dimensional principal component to estimate the likelihood, and the F bar contains the residual equivalent to the Euclidean distance. The complete likelihood estimate is written as a product of two independent marginal Gaussian intensities here, where PF is the true marginal intensity in F. P hat F bar is the estimated marginal intensity in the orthogonal complement F bar. Yi is the principal component, and the epsilon square is the residual. The optimal weight parameter mu is the average of the eigenvalues lambda I of F bar here. Considering a feature space of delta vectors, the differences between two images X, J, Ij, and Ik are modeled as a high-dimensional Gaussian intensity here. Our task is to seek the covariances sigma I and sigma E. The densities are zero mean, since for each Ij minus Ik, there is Ik minus Ij. And sigma I and sigma E are the covariances of omega I and omega E, respectively. Since the two distributions are known to occupy a principal subspace of face image space, only the principal eigenvectors of Gaussian densities are relevant for modeling. These densities are used to evaluate the same similarity score. To compute the similarity score, we need to compute delta and project delta onto the principal eigenvectors of intra-personal and actual personal Gaussians. Then exponentials are evaluated, normalized, and combined as a likelihood. This operation is iterated over the training dataset until the maximum similarity score is reached. For more details, please check with these references. Thank you. Bye.